So, good morning to all. As Andre said, today afternoon we will start 14:30 because of the football game of Brazil. So, but to the morning we will start with the seminar of Dominic Veconi. Currently, he is doing postdoc in ICTP. So thank you very much for accepting our invitation. If you can share your slides, please. So
yes, of course.
I will mention the title of your work. Thank you.
If I can figure out how to do that, then yes, absolutely. Maybe let me try doing it this way. Can I there we go. Okay. Can you see my slides?
Yeah, I think it's up here. So thank you. Dominic will talk for us about SRB measures and topological singular hyperbolic attractors. So Dominic, you will have 50 minutes plus 10 minutes of possible questions. Thank you.
Thank you.
Before starting, is it okay if we are recording?
Yes, of course.
Okay, thank you.
And also, of course, thank you very much, Puya, for the invitation. And of course, if you have any questions, if anyone has any questions during the talk itself, please don't hesitate to ask. I cannot see the chat when I'm sharing my screen in this way, so please do shout out questions if they come up.
I guess do.
So we're going to talk about SRB measures and singular hyperbolic attractors. And before we get too much into it, Wellington the other day yesterday gave a very good sort of description of some of the fundamental ideas of hyperbolic dynamical systems. But I want to start by sort of reviewing some of these main concepts for what we're going to look at today. So our setting is going to be a Riemannian manifold and some open subset U of that Riemannian manifold, and a function from U to the manifold itself that's a diffeomorphism onto its image. And in this setting, a compact F invariant subset lambda is called hyperbolic if there are constants lambda greater than 1 and C positive, so that for each point in lambda, there's a splitting of the tangent space into a stable and unstable subspace, which we denote by ES and EU. And they have the following three properties. First of all, this splitting is invariant under the differential of the map. In the stable space, the differential contracts vectors exponentially by this factor lambda. And in the unstable space, it contracts vectors in backwards time. And if you have these three axioms for this splitting, then we say that lambda is a uniformly hyperbolic set, or alternatively, that F is uniformly hyperbolic on lambda. And the simplest example of this is just a hyperbolic fixed point at the origin of a linear map or a linear flow from R2 to R2. In this case, the stable and unstable subspaces are, in the case of a linear map, indirect.
Sorry.
Yes?
Let me ask you something. We are observing just the first slide with the title.
That's you are?
Correct? Yeah.
No, you. Oh, sorry. So you cannot see that I'm currently flipping through slides right now.
No. So it's hanged on the first slide just by the title.
Well, thank you for informing me.
Now it's okay. Now it's okay. Again, it's on the first slide.
So
thank you.
So I can't full screen this very easily in that case, unfortunately. That's too bad. Okay, well, we'll just make do with what we have. We'll do it this way, I think, and that sort of is sufficiently full screened. And you can right now see this the second slide, right, where I define hyperbolic sets and things of that nature.
That's correct. Yeah.
Okay. Yeah. Thank you for informing me of that. So, like I said, the we're looking at uniformly hyperbolic sets, and this is a manifold generalization of the kind of picture that we expect to see for linear hyperbolic maps of R2, for example. And when you have this splitting, you also have what are called stable and unstable submanifolds. And locally, these are embedded disks, which we denote by WS loc and WU loc at each point X. That these disks are tangent to the stable and unstable subspaces. And also there are constants capital C, positive, and an alpha between 0 and 1, so that first of all, the stable and unstable subspaces are invariant under the dynamics, in that applying the dynamics to a stable subspace will send you to another stable subspace at the image point, and likewise for the unstable space. And the distance, rho here is the Riemannian, just the Riemannian distance function. The distance is contracted exponentially for points in the same stable leaf or stable manifold. And for points in the same unstable manifold, they're contracted in backwards time. And an example of something like this could be for a nonlinear flow. If you have a fixed point of a hyperbolic nonlinear flow, then the trajectories of that, the trajectories of points that are attracted to that fixed point or repelled from that fixed point are stable and unstable subspaces of that fixed point. And the point here is that in any coordinate neighborhood of these points, the dynamics looks more or less like this picture. So with this sort of characterization of stable and unstable submanifolds, there's a very famous example that I want to look at to sort of give a clearer idea of what this kind of thing can look like. Again, we're going to look at the solenoid map, the Smale-Williams solenoid, and this is a map that extends length in the direction of S1, and in the direction of D, in the solid disk direction, it's contracted, in this case by a factor of 1/5. And over time, successive intersections of this solid torus form this coiled, very complex topological object called the Smale-Williams solenoid. And it's an attractor for the dynamics, meaning that it's what you get when you take all intersections of iterates. There's a typo here. There should be an, can I write on this? I don't know if I can, but there should be an, I guess not. Oh, that's a signature. Never mind. Sorry. There's a typo, and there should be an N over that F in that bullet point. And the reason we care about this is that topologically, it carries all the information about the asymptotic behavior of the dynamical system. And this generalizes to attractors of topological dynamical systems. An attractor is a subset for which there's some open neighborhood of that subset, for which when you take iterates of that neighborhood, you get the subset lambda. Importantly, though, that lambda may not be unique. There could be multiple attractors for a given dynamical system. So the objective of dynamical systems and ergodic theory in general is to discuss the long-term behavior of dynamical systems. Now, we've seen one way to do that topologically. We saw that a topological attractor is a closed subset that is the intersection of successive iterates of a particular open subset. This is a way of talking about where points end up topologically, but does that attractor resemble every orbit? Are there some orbits that don't look like the entire attractor or only a part of the attractor? And to formalize that question a little bit, one thing we can look at is this notion of transitivity. So if you have a subset K of your manifold that is invariant under F, by this we mean that the mapping of K lands back into K, then F is transitive on K if for every pair of open subsets of K, there's some n for which f of n of one of those subsets intersects the other of those open subsets. So transitive dynamical systems are, in a certain sense, topologically indecomposable. You can't separate a transitive dynamical system into two separate systems that are more or less independent of each other. These are, these are indecomposable dynamical systems. And there's a similar notion in measurable dynamics as well. If you have an F invariant probability measure on M, and when we say F invariant in this case, what we mean is that the measure of preimages of a set is equal to the measure of the original set itself for every measurable subset, then we say that the dynamics is ergodic, that F is an ergodic transformation if every invariant subset K has either that the measure of K is 1, in other words, it's almost everything, or the measure is 0. So whereas transitive dynamical systems are topologically indecomposable, ergodic dynamical systems are measurably indecomposable. You observe only one major component of the dynamical system over long periods of time. So the reason that we care about probability measures in particular is because we want to look at the statistical behavior of chaotic dynamical systems. We saw yesterday that that some dynamical systems have sensitive dependence on initial conditions, and hyperbolic dynamics are in some ways the best model of this kind of behavior. But even though they have very hard to compute explicit orbits, in fact, it's usually impossible to explicitly compute a particular orbit, the statistical behavior is often quite regular. And when you think about statistical behavior, one of the most natural things to look for is the law of large numbers. To remind everyone, the law of large numbers just says that if you have a sequence of identically distributed random variables, then it satisfies the law of large numbers if the time average, the sum of 1 over n of all of the sum of all of these random variables divided by n, as n goes to infinity, that approaches the space variable, the space average, the expectation of these random variables. And if that happens almost always, then we have the law of large numbers for this identically distributed sequence of random variables. Note, I did not say independent, just identically distributed, because in practice, in ergodic theory, usually the random variables we're interested in aren't independent, but they are identically distributed, especially if you have that this transformation F is invariant with respect to the measure. And if you have a measurable real valued function phi and an F invariant probability measure on M, the manifold, then the sequence of observables given by phi composed with iterates of F, that's a sequence of identically distributed random variables for the probability space, the manifold itself. And so when we think about ergodic transformations are the best ones to work with from a statistical perspective in some ways, because if you have, this is a corollary of what's called the Birkhoff ergodic theorem, if omega is a compact metrizable space and F is a measurable transformation and mu is an F invariant probability measure with respect to which F is ergodic, then the set of all points for which this sequence of random variables satisfies the law of large numbers, in other words, for which the time average converges to the space average, has full measure. So ergodic dynamical systems are so useful statistically because they almost everywhere obey the law of large numbers. The problem, though, is that ergodic measures are in some ways quite exceptional. Most measures that you look at that are invariant under the dynamics aren't actually ergodic. So if you have an F invariant measure mu, its basin is the set of points where you do have this convergence of the time average to the space average. And by the way, just interpreting this a little more in a more sort of application forward viewpoint, you can think of the time average as the observed average of a sequence of experimental observations and the space average as the actual true behavior of whatever this random variable is. This is related to Boltzmann's ergodic hypothesis. So the basin of mu is the set of points whose long-term behavior is described statistically by the probability measure mu. Meanwhile, if you have a topological attractor, the largest open set of points for which those points get attracted to the attractor is the basin of the attractor. So whereas B mu, the basin of a measure, is the set of points whose long-term behavior is described statistically, B lambda, the basin of a topological attractor, is the set of points whose long-term behavior is described topologically by this attractor. And with this, we can now describe the particular measures we're really interested in. If you have a dynamical system of a Riemannian manifold with U some open subset, that's the domain of F, and mu is an F invariant measure on the manifold, and little m is the Riemannian measure on capital M. And typically that Riemannian measure is not F invariant. Then mu is a physical measure if the Riemannian measure, the volume of the basin of mu, is positive. What this means, in other words, is that the long-term statistical behavior is physically observable. So we call these physical measures if they have this property. But it's not just any physical measures we're interested in. We really want to know about what are called SRB measures. So what are those? Well, when we're looking at hyperbolic dynamics, what do physical measures actually look like? Which is to say, what are their supports? Well, if we want statistical behavior to line up with topological behavior, then we would expect those supports to be hyperbolic attractors. Now, I just want to remind everyone, when we saw the Smale-Williams solenoid before, and actually this is true for hyperbolic attractors in general, the local unstable leaves, the local unstable manifolds, are contained in the attractor. And that's very important if we want to think about probability measures that are physical and are supported on topological attractors. This motivates how we define what are called SRB measures. SRB stands for Sinai, Ruel, and Bowen, who are the three mathematicians and physicists who are sort of most credited with coming up with this formalization of these kinds of useful measures to begin with. So an F-invariant physical measure is an SRB measure if the conditional measures on the unstable leaves are absolutely continuous with respect to the Lebesgue measure on those leaves, on those submanifolds. So in the case of the solenoid, locally, the SRB measure can be thought of as a product of the Lebesgue measure on the circle and the Bernoulli measure on a Cantor set, because locally, that solenoid is a product of arcs, circular arcs, with a Cantor middle third set. But not all hyperbolic dynamics have strange topological attractors like the solenoid. For example, yesterday we saw the example of Arnold's cat map. There are some diffeomorphisms that are uniformly hyperbolic everywhere on the compact manifold serving as their state space. And those diffeomorphisms are called Anosov diffeomorphisms. And if those diffeomorphisms are uniformly hyperbolic everywhere, then the SRB measure is equivalent to Lebesgue, assuming that the with other certain regulatory assumptions on the manifold itself. On the dynamics of the manifold. Equivalent to Lebesgue, meaning that there's some density with respect to Lebesgue. I think I may have made a typo in here, but the idea remains more or less that that if you have a uniformly hyperbolic map that preserves area, then that area is an SRB measure. And these have been studied quite a lot in the past few decades as sort of the main sort of centerpiece, or one of the main centerpieces of smooth ergodic theory in general. It started off with Sinai, Bowen, and Ruel in the 70s, who collectively showed that if you have a compact manifold, a C1 plus alpha diffeomorphism U onto M, and a subset that's uniformly hyperbolic given by the topological attractor of U, then there are in most finitely many SRB measures on lambda. Furthermore, if you have that F is topologically transitive on the attractor, then there's a unique SRB measure on the attractor, and the basin has full measure in the open set U. And in some sense, SRB measures are very natural to talk about, but they're actually quite exceptional. And if you generalize notions of uniform hyperbolicity, then proving the existence of SRB measures can be quite challenging, sometimes not possible. For example, in 1995, Hu and Lai-Sang Young found an example of a hyperbolic diffeomorphism of the torus that's actually non-uniformly hyperbolic. And when I say non-uniformly hyperbolic, what we mean by this is that the rate of expansion in the unstable direction is non-uniform. It slows down to 0 at the origin in particular. But they showed that this diffeomorphism does not emit an SRB probability measure. So they're quite exceptional. But they are related to transitivity in a pretty neat way. And it was shown by Federico and Hannah Rodriguez-Hertz, Ali Tatsibi, and Raul Urez in 2010 that if you have a topologically transitive Hilbert diffeomorphism of a surface, then that diffeomorphism admits at most one SRB measure. This does not guarantee the existence of an SRB measure in the first place, only that there's at most one of them if your map is topologically transitive. Okay, so with that, let's talk about singular hyperbolic attractors. So at this point, we need to say what exactly our setting is that we're working in. So once again, we're working on a Riemannian manifold, and we consider an open and pre-compact subset K and a closed subset N of K. And when we say N plus, we're going to use N plus to denote N with the boundary of K. And we consider a diffeomorphism F of K without N onto K as a diffeomorphism onto its image. Now, N minus will be used to denote the set of all points that are continuous or images of continuous extensions of F to N plus. And we'll see what a concrete example of that looks like in a little bit. And furthermore, we're going to talk about K plus. K plus is the set of points that never fall into the singular set. And then D is the set of all intersections of, or rather, it's the intersection of all forward iterates of K plus, and lambda is its closure. Now, K plus we need to talk about because there are possibly points that fall into the singular set, and we don't want to include those points. So D is the set of points for which the map is defined for all time forwards and all time backwards. And lambda, its closure, is the topological attractor. And we say that lambda is a singular hyperbolic attractor if there is a continuous splitting over K minus N into stable and unstable subspaces of the same kind that we saw before. We saw that vectors are contracted in the stable direction and expanded in the unstable direction, or contracted in backwards time. And let's look at an example of this. So the simplest example, or perhaps the most classical example, is the geometric Lorentz attractor. And this is a map of the unit square to itself. The singular set is the horizontal axis. And F is a diffeomorphism onto its image that's given in coordinates by phi and psi, where phi and psi satisfy this hyperbolicity property that phi x and psi y inverse both have norms less than 1. And also, if you take the limit as y approaches this horizontal axis, then the image of that limit gets collapsed to a point f0 minus, and that should say y descending to 0, not y descending to y. That's silly. If you take the limit as y goes to 0 from above, then you get a different point f0 plus. These are constant points. So in this case, thinking back to the definition we saw earlier on, the vertical lines, the foliation by vertical lines of the units of this unit square, form the unstable distribution EU, and the horizontal lines form the stable distribution where lengths and vectors are contracted. Meanwhile, n minus, let's go back and see what this is for a second. N minus we saw is the image of continuous extensions of F to the singular set. So in this case, n minus is the pair of those two red dots. So if you take this blue rectangle below and collapse the red line to a dot, that becomes the triangle, the blue triangle on the right, and likewise for the green rectangle, collapsing the red line to a red dot, then that becomes the triangle on the right-hand picture. And the reason we're interested in this is the Poincare first return map of a transversal cross-section of the classical flow for the standard Lorentz attractor. And many properties of the Lorentz attractor, the original one, have been sort of discovered and explored using this Poincare first return map in the geometric model. And you can generalize this to lots of other kinds of first return maps that are of Lorentz type. So Lorentz type map is more generally any kind of map where you have a sequence of finite collection of horizontal lines, and with certain regulatory conditions on the differential, you have that f is again a diffeomorphism onto its image, and that each of these lines get collapsed to single points when you apply the dynamics to them, and then or apply continuous extensions to the dynamics to them rather. And you have this hyperbolicity property of the components of f. And these are quite persistent in persistent in the sense that there are very many of them in the space of all singular diffeomorphisms of manifolds. So this is a result of Aframovich, Bykov, and Shilnikov, who showed that if M is a compact Riemannian manifold of dimension greater than or equal to 3, then there exists a vector field and some smooth submanifold for which the first return time induced by f on this submanifold S by your flow is a Lorentz type map. So these are very common and ubiquitous examples of singular hyperbolic diffeomorphisms or singular hyperbolic maps. But not all singular hyperbolic maps arise as first return maps of flows. For example, the Losey attractor is an example, which has this formulation. You take a tent map, x maps to 1 minus a times the absolute value of x, and you perturb it by a small number b. And actually, this is topologically conjugate to the Henon map. For those of you who are familiar with the Henon map, for those who aren't, the Henon map looks very similar to the Losey attractor, only instead of being an absolute value, it's quadratic. And the Losey map, unlike the geometric Lorentz attractor, does not arise as the time one map of a hyperbolic flow. So the main result that we have, first of all, let's talk about our setting. Again, just to remind everyone what the formalization of all of this is, we have a Riemannian manifold M. K is an open and pre-compact subset, and N is closed in K. F is a diffeomorphism onto its image, and N minus is the image of continuous extensions of F, the diffeomorphism, to the singular set N. And as we saw earlier on, in the case of Lorentz type maps, that N minus is a finite collection of points that come from the collapsing of those horizontal lines. And lambda is a singular hyperbolic attractor with some expansive constant lambda greater than 1. In 1992, Yakov Pessin showed that if you have F satisfying these conditions and you have a singular hyperbolic attractor lambda, then after imposing certain regulatory assumptions on F, there are at most countably many ergodic SRB measures supported on lambda. I heard a sound effect. Does someone have a question?
I think no. You can continue. Thank you.
So so it was shown before that that singular hyperbolic attractors in general admit at most countably many ergodic SRB measures, but with certain assumptions we can actually show there are finitely many, and those assumptions are this. First of all, the singular set N is a disjoint union of finitely many closed submanifolds, N1 through Nm, of dimension equal to the codimension of the unstable submanifolds. The local unstable submanifolds intersect the singular set transversally with an angle uniformly bounded away from 0. And also that the image of the singular set, rather the image of the n minus set doesn't fall back into the singular set for sufficiently long time. How long? Well, up until some point lambda to the L, up until some time L, where lambda to the L is greater than 2. Lambda, remember, is our expansive constant. The last thing we require is that the the stable foliation, in other words, the WS loc manifolds, are locally continuous. In other words, the local stable curves, and in particular the length of those local unstable curves, vary continuously with your point Z. And I just want to point out also that these assumptions, 1, 2, and 3, disjoint union of submanifolds, unstable curves intersect the singular set transversally, and long recurrence until you get back to the singular set, those are all satisfied in the geometric Lorentz attractor, right? We can see that the unstable foliations, or the unstable submanifolds, are vertical lines, and they intersect the singular set, this red horizontal line, transversally, for example. And of course, there's only one component of the singular set, so it certainly satisfies the finitely many components axiom. And if you have all these assumptions, then actually we can show that the attractor admits at most finitely many ergodic SRB measures. But not only that, if F also satisfies assumption 4, this notion of local continuity, that the local stable curves vary continuously with your base point, then there's a finite collection of F invariant subsets, lambda 1 through lambda n, which are clopin in the attractor lambda, and each supports a unique SRB measure. In particular, what this means is that if you have that F from lambda to lambda is transitive, if it's topologically transitive, then actually F admits a unique SRB measure in that setting, provided that you have this local continuity property. Now, this is not the first time that that results on finiteness of singular hyperbolic attractors have been explored. Before I go that far, I just want to point out that this means in particular that both the Lorentz type maps and the Losey map admit finitely many SRB measures.
That's my question. The third condition here, both of these maps are satisfied, yeah?
Yes.
And in Pessin's work, also this third option was a condition as well.
Which condition? This.
I mean the Fk n minus intersection of n equal empty set.
Yes. So all three of these conditions do appear in not this result of Pessin's work, but a related one, and in the same paper. So yes, these do appear. However, I will. Let me get back to this question in a little bit, because I'm gonna talk about this in a couple slides.
Okay. Okay. Thank you.
Yes. So so before going that far, I just want to point out that assumption that n is a finite union of submanifolds really is required. You can't relax the condition that n is a finite union, because if n has infinitely many components, then it might not work out. So for example, you can take a countable number of horizontal lines in the unit square, and in each resulting section, you can embed a copy of the geometric Lorentz attractor. Well, each of those sections admits its own SRB measure, but there are infinitely many of them. And the reason that it doesn't work out in this example is because the proof of the main result requires a lower bound on the distance between the components of the the singular set. And in this example, if you just stack up a bunch of geometric Lorentz attractors up against each other, we don't have a lower bound on the distance between the components of the singular set. Now, to Puyo's question, in the same year, Eugene Satayev also showed that there are finitely many ergodic SRB measures and finitely many disjoint invariant sets that each of which support one of those SRB measures. But Satayev's result does not use the topological assumptions on the attractor that we mentioned earlier on. Satayev uses different regulatory assumptions on the recurrence of the dynamics. So in particular, we require, Satayev requires that the volume of backwards iterates of a neighborhood of the singular set is bounded in a particular way. And also, if you take V to be a manifold that's tangent to the unstable cone, and what I mean by that, I should have pointed out what cones mean in this case, but the unstable cone is a cone in the linear algebraic sense around the unstable direction. And if you have a manifold that's near the unstable direction, then backwards iterates of this neighborhood with that unstable cone are also bounded in the volume on that on that submanifold. And if you have these regulatory conditions on the recurrence, then you also have disjoint invariant subsets and ergodic SRB measures, and only finitely many of them. Now, what Pessin showed in his 1992 result was with these three assumptions that we mentioned earlier on, that in 2 dimensions, specifically in 2 dimensions, these assumptions imply the recurrence hypotheses of the previous theorem. This is so these assumptions do appear, and by virtue of Satayev's result, they do give us finitely many ergodic SRB measures in dimension 2. However, those assumptions actually give finitely many SRB measures in any dimension. And they don't, and not only that, but you can avoid having to use recurrence hypotheses that are too complicated to really check very easily in the in this setting. The downside, though, is that these assumptions don't give existence of SRB measures in dimension higher than 2. They only abound on how many of them there can be. So Puyi, does this answer your question?
Yeah, exactly. Thank you.
Okay. And there have also been a lot of results over the last couple of decades in singular hyperbolic flows. So I mentioned this briefly earlier on in the context of Lorentz type maps. So if M is a 3-dimensional Riemannian manifold, you can consider a CR vector field X with flow XT. And we say in this case that a compact XT invariant subset is singular hyperbolic if, first of all, lambda is partially hyperbolic in the flow. In particular, this means that we have an invariant splitting into a stable subspace and a center unstable subspace, for which the flow is contracting in the stable direction, volume expanding in the central direction, and the stable direction dominates over the central direction. So the formalizations of those ideas are given here. Contraction meaning contraction in the in the sense that it contracts vectors by lambda, and also we have volume expansion in the central direction, meaning that the Jacobian of the flow is expanding. So if you have this partial hyperbolicity for the flow, and also if all singularities of X contained in lambda are hyperbolic, then lambda is a singular hyperbolic attractor. And here in this case, singularities does not mean that it's discontinuous like it was in the discrete dynamics case. Singularities here just means that these are fixed points of the flow and they must be hyperbolic. And the standard Lorentz system is one example of such a flow. The origin is a hyperbolic singularity of the standard system of Lorentz differential equations. In the setting of singular hyperbolic flows, First, the first major result, two major results. First one was from Maria Jose Pacifico and Morales, who showed that a singular hyperbolic attractor for a flow with dense periodic orbits and a unique singularity is a finite union of transitive sets. And under the very general assumption of being Kupka-Smale, this union is actually disjoint. Kupka-Smale means that the closed orbits and the critical points are all hyperbolic, and also the stable manifolds of a critical point can only intersect the unstable manifolds of another critical point transversally, not tangentially. So it's a very nice setting to work in for hyperbolic flows. And then later on, Vitor Araujo, Maria Jose Pacifico, Enrique Pujals, and Marcelo Viana showed that a transitive attracting set, whose existence was shown by Pacifico and Morales, supports a unique SRB measure, in fact. And in this, for flows, this means a physical probability measure which disintegrates to an absolutely continuous measure along center unstable leaves. Versus just the unstable manifolds in general for the discrete case. And one consequence of these results is that if you have a singular hyperbolic attractor for a flow on a 3-manifold with dense periodic orbits, then you have the following spectral decomposition. In other words, you have that the attractor is a disjoint union of flow invariant transitive compact sets lambda 1 through lambda k. And there are k ergodic SRB measures that are each supported on one of those lambda i's. And every other SRB measure is a convex combination of those mu i's. In 2010, Eugene Sataev generalized this to singular hyperbolic attractors in any dimension whose stable direction has dimension n-2. And very recently, in this year, Vitor Araujo posted a preprint on arXiv that showed that if you have a vector field on a 3-manifold and a singular hyperbolic attractor, and SL is the number of hyperbolic singularities, then actually the number of ergodic SRB measures whose support contains a singularity is bounded by 2 times the number of hyperbolic singularities. Okay. So in the very little time I have left, I want to say a little bit about how one could go about constructing the SRB measures. This construction works in 2 dimensions. This construction does not give this construction does not give SRB measures in higher dimensions necessarily, but the at least not without. Well, actually, let me rephrase that. This does work in higher dimensions if you have additional regulatory assumptions, but those regulatory assumptions may not be met in dimensions higher than 2 given our assumptions. But this is still, I think, useful to show how one can go about constructing SRB measures in the first place. So the first thing we want to consider are the global unstable leaves. These are the union of images of backwards images of unstable leaves for different z in the for different points z in the domain. And we consider the Riemannian leaf volume M and the Riemannian distance rho on each leaf, on each unstable manifold WU. And we consider U0 to be the ball of radius r for an appropriate r, centered at z in the unstable leaf, and UN is going to be iterates of that. Is going to be the iterates of that U0 each time deleting inductively each time deleting the points in the singularity. And we denote by JU the determinant of the differential. In other words, the unstable Jacobian at different points z, and it has to be the unstable Jacobian because we care about the expansion for this to work. And for each y in WU, we consider the infinite product of the ratio of the Jacobians at different backwards iterates, where this function is defined. That kappa, this infinite product of the ratio of expansions, forms the density that we're going to use to define our SRB measures. So, so we're going to consider nu n tilde on each of these subsets un, given by a density times Lebesgue measure, and Cn tilde is a normalizing factor to make this an actual probability measure. And without the tilde, nu n is just going to be a measure on lambda that's given by all intersections, or that measures intersections of subsets A with un for Borel sets A. And we define the empirical average, or mu n is just the average of all the nu k up until point n, and until time n. And after you take this average, the final step in the construction is to show that mu n has an F-invariant weak limit measure that's concentrated on D. Remember that D is the set of all points that have full definition forwards and backwards. And mu may, of course, what that weak limit measure is, that might depend on our initial choice of reference point Z. And even...
Dominic, sorry, about this set D, does it have anything to see with n plus union with n minus?
I'm sorry, can you repeat your question?
I'm asking about set D.
Yes.
Yeah. What's the relation with n plus and n minus?
So I really wish I had a pen that I could write on this. Let me go back a little bit to the setting. So not that one. So D. So first of all, just to remind everyone, it's good to be sure that we're aware of what the of what all this stuff is, because there are a lot of sets we need to be careful of when looking at singular hyperbolicity. K plus, first of all, K plus are all of those points that never fall into N plus. K plus, in other words, are all the points with full forward orbit. And then
okay, yes, the complement, in fact.
Well, yes. Not just the complement, but the complement for all time forward. So D, in other words, is the largest set for which the dynamics is defined for all time, forwards and backwards.
Exactly. I was thinking that is the union of all singular sets, or
No. D is the good set.
Okay, thank you.
No problem. Thank you for clarifying that. Yes. So let's see where I was. Okay. So the Pui, about how much time do I have left?
I think 2 minutes.
2 minutes.
2 or
Okay.
3 minutes.
All right. The I'll in 2 minutes I'll say quickly what the idea is. So the first thing that we so the idea basically is with this definition, we're going to consider a convenient subset. I'm not going to spend too much time defining what this subset is, but we consider a convenient subset B delta minus. B delta minus are those points that have sufficiently large unstable leaves, whose unstable leaves are allowed to be long enough before they bend around and have weird topological properties. So with that, B minus delta, the idea is to show that there is okay, I don't really have time to go into this part, but that's too bad. Let me just say really quick in the last 2 minutes that I have okay, so there's a 2-step procedure for proving our main result. We have this set B minus delta, which is a set that tells us about the size of the unstable manifolds for different points, and and as delta gets smaller, B minus delta gets larger, because the smaller the idea being that if you have a smaller unstable leaf, then you can still have even smaller unstable leaves, but you can't necessarily have larger ones. So the idea is to show that there's some delta, some sufficiently small delta, so that B minus delta is given positive volume for every ergodic SRB measure. So if you have an ergodic SRB measure, then it's guaranteed to put positive weight on this B minus delta naught. Once you have that B minus delta, then the problem is, okay, show that that B minus delta can only have finitely many SRB measures, because we can restrict our attention now to just this one set, B minus delta. To do that, we use what's called a Hopf argument. And to really quickly say what the idea here is, because this goes back to some of the ergodic theory stuff we were talking about at the beginning of the talk, what we care about are those points where the forward and backward time averages exist for every continuous function. They may not be constant, they may not be equal to the space average, but at least the functions themselves exist. And the Birkhoff-ergodic theorem, what it really tells us is that almost everywhere, these averages are guaranteed to exist. Now, if you're in the same unstable space, then going backwards, you're getting close together. So phi minus, the backwards average, is constant on unstable leaves, on unstable manifolds. And the forward average is constant on stable manifolds for the same reason. On the same stable manifold, you get closer together. So the phi, so phi plus is constant, the forward average. At this point, you use what's called the product structure of the stable and unstable leaves. The stable and unstable leaves, like in the examples that we saw earlier on, form a kind of type of coordinate system in the manifold. And with that coordinate system, with certain regularity assumptions, the idea is to show that since this subset B minus delta has a full measure set that's closed, you can partition that set into equivalence classes based on how much, based on whether or not the backward and forward averages for every function are constant. This is the idea of what's called a Hopf argument. So the point here ends up being that every SRB measure is supported on exactly one of those equivalence classes, and every one of those equivalence classes must support exactly one SRB measure. And that tells us that there can only be finitely many SRB measures because we're working in a compact set, and each of these equivalence classes end up being clopen in B minus delta, or in an appropriate subset of B minus delta. Okay, that was a really bit of a crash course through the end of the proof here. Sorry that I couldn't go into more detail with this, but thank you again for giving me the opportunity to share some of this with you guys. So thank you very much.
Thank you very much for your nice talk. First of all, thanks, Dominic, please open your microphones, and thanks, Nick. Thank you very much. So